In this video, we're going to take a look at how we can use recursion with linked lists. So in one of my previous videos, we introduced this concept of recursion. And if you haven't had a chance to watch that video, then I'd recommend watching it before you watch this video. And I'll put a link to that video in the description of this video. So it's right below this video. So we said that recursion was this problem-solving strategy or this problem-solving technique for breaking larger problems into smaller problems of the same form. And we also looked at some examples of recursive structures that you may find in nature. So we saw a tree, ice crystals, I think a shell. So in all those cases, we had these larger structures that were composed of smaller structures of the same form. And we also have recursive data structures. And one of those recursive data structures is the linked list. So let's take a look at this linked list that we have here in a little bit more detail and see how it is, in fact, a recursive structure. So this linked list is a 3-node linked list. We can easily see that. But you could also think about this linked list that we have here is containing a smaller 2-node linked list that just simply has Mark and Tom, and that 2-node linked list of Mark and Tom containing another single-node linked list just containing Tom. So we have this larger structure here that's composed of these smaller structures, these smaller linked lists that are of the same form. So it really is a recursive structure. And so if we have a recursive data structure, we can think about using recursive functions to process those particular structures. So let's look at how we'd write a recursive function to process this linked list. So let's first think about what we did with a iterative solution for being able to process a linked list or to be able to traverse over each node in our linked list. What we did was we set up this pointer to initially point to the head node. So we had this current pointer here, and it just simply pointed here to the same node that head pointed to, and we called it cur, short for current. And what would happen is on each iteration, we would update the value of cur to just simply be cur's next. So we had set cur's next to cur, and that would allow this pointer here to point to each successive node until we finally got to the very end and current was set to null, and at that point in time it would kick us out of our looping structure. And we really have the same sort of idea almost with the recursive function for being able to process a linked list. Except this time we're going to think about this current pointer existing as a formal parameter. So let's assume that we're trying to write a recursive function maybe to print out our linked list. So what I'm going to do is just start writing the code for that right below our linked list representation here. And we'll say that it's a void returning function. So we're going to simply just print out the contents of our linked list, and we'll just call it print list. So we have print list here, and we'll pass to it a node pointer. So we have a node pointer being passed, and we'll just call it cur, just like in our example here, or just like what we have specified here. And then we have to start thinking about our base case and our recursive case in the body of this recursive function. So the base case would be whenever this current pointer here is pointing to null. At that point in time, we don't have anything left to process, no other nodes in our linked list. And in the case of our base case, we really don't want to do anything. We just want to simply return from our print list function. So there's actually nothing to do in our base case. And it turns out that if we're not in our recursive case, we would be in our base case and we'd simply return. But if we're writing this function, we really don't even have to test for our base case because we'd return automatically if we're not in our recursive case. So let's not even worry about writing anything for the base case and just focus on writing the recursive case. So for the recursive case, we'd be looking to test to see if what? If our current pointer was in fact not equal to null. So if it's not equal to null, we know that we're in our recursive case. So in the recursive case here, what do we have to do? So one thing that we'd have to do is print out the contents of our node. So that would be just a cout statement. So we could say cout, use our insertion operator, and we'll assume that this insertion operator is overloaded. So we'll do cout insertion operator, and then specify, well, we would have to do a dereference on our pointer. So dereference our current pointer, and then maybe have another insertion operator and do an indel. So that would be the actual processing of our node, depending on whatever current was actually pointing at. Now the other part that we'd have to have in here for our recursive case is the actual recursive call. So if you're not doing a recursive call, you don't have a recursive function. So in this part here, for the recursive call, we know that we'd have to specify the name of our function, which would be print list. And then what do we want to do? Well, we're going to be passing in a node pointer but we want to be driving this current pointer forward to the next node. So the way we go about driving it forward in a recursive function is by just specifying here curs next. So we specify curs next here. So this curs next is going to be specified. And if we do that, check it out. Curs next is going to be passed here to cur. So that's the same thing as what we were doing really with the iterative approach by using a looping structure, using a while loop. So we said as long as, or as while curs not equal to null, keep processing and keep setting curs to curs next. Now we're doing the recursive approach where we have here the node pointer as part of our formal parameter list, and we're just passing curs next here to cur. So at some point in time, cur will in fact point to null. It will test for that here in our recursive case, find out that that's not true, and we'll just get kicked out of our print list function. So one thing that I want to emphasize again is that every single time that we're calling this print list function, we are in fact chopping off a little bit more of our linked list to deal with. So we're dealing with a smaller and smaller linked list structure on every single subsequent recursive call. So in this particular case, using a recursive function really doesn't necessarily bias anything over using an iterative approach, so just using a looping structure. And in fact, using the recursive approach would in fact require more resources because we're having to allocate a new stack frame every single time that we do this recursive call here. So every time we do that recursive call, we get a new stack frame and all of our local variables get allocated all over again. So what I want to do now is quickly illustrate what would happen on our call stack as we executed this recursive function called printlist using this linked list here as our example. So the first thing that would happen whenever we first call printlist would have an allocation of a stack frame, and I'm ignoring our main stack frame, but certainly there would be a main stack frame or whatever function actually called this printlist function. And what would happen is we get the address of head passed into this function. So I'm not going to depict all of that, but cur would simply hold the same address as head. And what would take place here is we'd print out the contents here. So notice the ordering here of our operations. Our first operation in our recursive case is to print out or to see out whatever cur is pointing to. So we're doing a dereference on cur. We're assuming that we've overloaded this insertion operator. So we'd print out April. So we'd do a print on April here, and I'm going to just keep track of what we're printing out up here above our linked list. So we'll say that April's been printed out, and then what would happen is we'd have a recursive call. So we'd do a print list here, and then we would, I don't have much room, so I'm going to just abbreviate this C, and then arrow, and then do N for next. So we'd then pass in curs next. So then our current pointer, so first it was pointing here, and now it's going to be pointing over here. So it's going to be pointing here now. So we get a new stack frame. So we get a new stack frame here. Let me try to draw it a little bit closer to the way it should be. So we get a new stack frame. And what we would do that time is just print out what? We'd be printing out not April, but printing out Mark, since our cur pointer is now pointing to this node here that has Mark. And then we'd do another print list. So we're doing another print list here and passing in curs next using my little abbreviation there. So now current would now be pointing over here to our Tom node, and we would get another stack frame. Yeah, and this is, I guess, kind of maybe boring. You see the picture of what's going on here, but I'm going to make a point in a bit. So we'll do a print here, and this time we'd print Tom. So, oops, I forgot to do Mark. So Mark would be up here. And now we're printing Tom, so we'd print Tom out here. And then we'd do another recursive call, so we'd do print list. And this time we'd have the currents next being passed in, and this time's currents next is going to be null. So whenever we do this and have our next stack frame up here, what's going to happen? Well, in this particular case, we'll see that cur is not equal to null. So at that point we'll return. What do we return to? We would return to this point here. So I'm going to go ahead and pop that off, and then we would go about popping this off. So we would simply return because there's nothing left for us to do. We've finished executing. So what happened is this print list, this recursive call was the last thing that we did inside of this recursive case. So since there's no other statements in this particular function to do, it would just simply return. Where does it return to? It returns to the previous stack frame. So we would get rid of this, and it's the same case there. And then we would get rid of this. This would be popped off of our stack. And then finally, this would be popped off of our stack. Now, the interesting thing is the order that we have these particular statements. If we would have switched the ordering here, we'd have got our linked list, or at least our nodes, the contents of our nodes, printed out in exactly the opposite order here. So I think that, I don't know, maybe I'll start that and just to show you exactly what's going to happen here. Alright, so what I want to do now is simply swap these two statements around so that we're doing the recursive call first, and then we're doing the processing statement. In our case, the processing statement is just to output the contents of our node. So let me see if I can move these two statements around with not too much work. So now we've readjusted those two statements in terms of their order. So it's going to be the same basic idea, but check out what happens. Whenever we create our first stack frame, so this is our first stack frame. Whenever we first call print list, we'll have a recursive function call first. So we'll have to do our print list here, print list, and pass in currents next. And then once we finish that, we can actually do the print statement where we could actually print out, in this case, April. But April will not be able to be printed until we actually are unwinding the stack here. So we get another stack frame. So the first thing we do is this recursive call, the print list call. So that would make another stack frame come on board here, or pushed onto our call stack. And it would have what? Another recursive call where we do a print list. So we do a print list of curs next. And then the second statement we do is just do a print of mark. But again, mark cannot be printed out until we're coming back, until we're unwinding. So the point that I'm trying to illustrate here is that if by just swapping these two statements around, we're able to actually print out our list in reverse order, because the topmost stack frame will be the one in which we would print out first, because it would be the first one that we would come back to after hitting our base case where the value is null. And I'm not going to go through all of those steps. Hopefully you can see it. Maybe you can work that out for yourself and continue drawing these pictures. But it's really cool in the case of a recursive function, just by swapping these statements here, the processing statement, or excuse me, the recursive call statement and the processing statement around, how you can get a different ordering in terms of how you're processing stuff because of the stack-based nature of these recursive calls. So that's the main thing that I wanted to illustrate in this video. But in an upcoming video, we'll look at implementing this print reverse list function in the contact list project that we've been working on. But the implementation for that is going to require some details we haven't discussed yet, but are really important whenever we're dealing with recursive functions or implementing recursive functions in a class. But that's all for this video.